In the summer of 2014, I spent a semester at the Leibniz University of Hanover as an exchange student. During my time there, I worked at the Institute of Microproduction Technology at the university where I was supervised by a research associate. Her name is Miriam McKean. I accomplished most of my work at a clean room facility. I'm going to tell you what the clean room is. This is a sealed laboratory used for microsystem production and nano fabrication. So it's an exclusive and very sealed laboratory where the atmospheric pollutants in the air is monitored and is kept to minimum. The laboratory I worked at is classified grade 100, which means per cubic feet there is no more than 100 particles which are of the size more than 0.5 micrometer. Human hair is 200 micrometer, which means a particle which is 200 times human hair were not even there in per cubic feet. So that's the sense of that's the sense of a clean room. You need that kind of cleanness to do your work. And, by the way, this picture I was not doing actually anything, just for modeling. So I worked under a bigger consortia called Planner Opto-electronics System, funded by the German Research Foundation with a budget of around 10 million euros, who are trying, it's a consortia of 4 different German institutes, of which University of Hanover is a part. They are trying to develop a novel, printable, flexible opto-electronic system. I'm going to let you know all those terms. So as you can see, I mean, if you have an electronic device, most of them are rigid. So if you ever break an electronic device open, you'll see there's a rigid circuit board on which there are plenty of chips and other electronic components all working together to give you something useful, like your mobile phone or your camera. The future is to have like your iPhone 6 to bend, iPhone 10 to bend in your pocket, or you can have microsystems that you can install on your jacket that will probably take sunlight to charge your mobile phone while you're walking, or your iPad, everything. So the future is actually essentially flexible electronics. As you can see, there's a lens that has been developed at the University of Washington. They put it on a on a rabbit eye to enhance its vision and everything. So we essentially need to develop a technique to connect your semiconductor chips on flexible materials, for example, polythene or PMMA, plexiglass, something polymer based. But in reality, if you are working with rigid objects, you can take the chip and the substrate, put some metal in between because you want electrical conductance. You heat them, you press them, they melt, you let them cool, they stick together. But if you have a polymer like a polythene or plastic, you cannot treat it the same way you treated a silicon bar because they have low thermal budget, less heat tolerance. So something has to be developed, and that was my project, to develop something so that we could get those chips on flexible material. At that institute, Institute of Microproduction Technology, they use the metal I talked about that you put in between. They use eutectic compounds. Eutectic compounds are a mixture of 2 or more elements that melt at a lower temperature than the individual components. So they put indium tin as a combination. Those are 2 elements, tin and indium. I'm not going into the chemical properties of them, but they used it with silicon chip on silicon substrate. And the temperature at which they could do the work exceeded the temperature, the tolerance temperature of plexiglass that I chose to use, which is chemically called PMMA, polymethyl methachloride. So which means we could not do the same process on PMMA. So something had to be done. So they came up with the idea that if we could substitute the heat energy with ultrasonic energy, we can get it done. Ultrasonic energy means something which has frequency range in 20 megahertz. Human can hear up to 20 kilohertz, so this is something you cannot even hear when you apply it. Your radio stations, televisions, I think they work in the order of 100 megahertz, like radio channels 99.9 FM, stuff like that. So that's why you do not hear your radio waves whopping around, but actually they're all over around you, just don't see them or even hear them. So I chose PMMA, as I said, it's opto-electronics, which means you want to transmit your data in the form of light, and you know light travels fast, so you can have huge amount of data transported or transmitted at a very fast rate. So I need something that will let light go through. So PMMA is very transparent, good optical clarity, so I chose it to be my substrate. But the chip still had to be semiconductor because that's the way it works. I never worked in a clean room facility, so I had to be trained a couple of weeks before I could do my job. So we took silicon wafer, as you can see on the right. I coated them using some technique. It's called like electron beam vapor deposition. Then we diced them, made my. There's a fake chip because chips are expensive. I cannot work my research with original chips. I made my fake chips, and then I also created my substrate with coating that with the chemicals I said, either Indian tin or Indian bismuth. And then I put. So this is my chip. This is my substrate. I put them together. I heat underneath. I put pressure and ultrasonic sound at the same time, and I let them join together. But the whole point of the experiment was to find out the right amount of heat, right amount of ultrasonic sound, right power, and all those parameters to figure out. I can show you a video, a couple of videos to show actually, help you visualize how the thing works. So I put my chip, that's the chip, upside down, that's what it's called flip chip, and then a probe comes down. This is a machine, it's an industrial machine they use that suck the chip with the air pressure and picks it up, and then I put my substrate that looks like that over there, and then the probe brings down the chip that was earlier picked up, it pushes onto it. By the way, the sound you're hearing is not ultrasonic sound, it's the mechanical sound of the sound. And the heat is coming underneath, it's a heat plate, and then the bond is formed. But the process takes much longer and there are much more things to do, but this is just a fake, again, a fake thing to show you. But those are the samples, how they look like once I coated them, and if you can see under microscope, it's just 5x times a very homogeneous layer of layering, which was very much needed for the bonding to take place. If you have like non-homogeneous layer, they won't mesh together well. This shows, this is an interesting week I spent because I never did extensive laboratory work before. So one thing I learned from this was research do not work the way you want it to work. You have to expect anything. When I was doing the coating, I wanted the right hand side, but it happened to be the left hand side, like island formation. And I got mad, and at that point my research could end because if I could not fix it, I would not proceed, right? So it would not be a successful research. They spent about a week to figure out why that was happening, and I figured out that it was like I did not put certain parameters correct, and I did not speak German. I still don't speak German when I went there, but the machineries were mostly in German, so there was some communication barrier between me and the machines. My supervisor helped me with that. So it was an interesting thing to learn for me as a young researcher that you do not expect things to work the way you want. So it would be a big risk if I go for graduate school in research that I might end up with a degree if my things don't work. 7 years wasted, right? As I said, my goal was to find each parameter. So there are 6 parameters that I wanted to find. So if I do trial and error, you have to do it 720 times to figure it out. I didn't do that much. I used my physical intuition, like what would make sense to choose as a right temperature. Like, for example, the maximum temperature could not be any arbitrary temperature. It had to be something lower than the transition temperature of the PMMA. Otherwise, if you go beyond that, the thing will be melted. So I'm not going into details, it will take time, but that's how I mostly designed the experiment, and then I went forward with the implementation. This was for the Indian team. I also did another experiment with Indian bismuth, but same idea. Once you have done the bonding, you have to figure out if the bonding is strong enough. So I had to do electromechanical evaluation of the test, evaluation of the bonding. I mean, if you have a product that doesn't work because they go off, well, it's not a good idea. So I did shearing. Let's say I provided a horizontal force and see when it breaks, and then recorded the data and compared with the US military standard 883G to see if it satisfies their requirement, then it's good to go. That's how I evaluated my thing. These are some of my results. As you can see, I varied one parameter when I got the highest strength in the bond, I stopped and I moved on to the next parameter. You can notice one thing, I have not put any numbers in there. I'm going to tell you in a bit why I didn't, but that was essentially the idea, to choose the highest result for one parameter, then move on to the next, and then move on to the next, and find the right combination. This is for the Indian Bismuth case. So finally, in conclusion, I could say that we actually were successful and we got a novel result that yes, it's possible to have chip mounted on flexible polymer-based substrate. And since the work is novel enough, we were able to write a paper and it's under peer review now in IEEE's journal. And that's the reason why I didn't put any numbers in there, because for a non-distribution thing I signed, I committed to. So yeah, finally a co-author. And during my trip, during my internship, I was able to go to certain engineering facilities in the city and in the country, included Volkswagen and Airbus. It was nice for me to see how engineers and scientists work in corporations and still make money and a livelihood. I have to do at some point in time. It was great to be. And at the end, this was my conclusion. And when I came back home, came back to the United States, I'm not from the United States, but I still call it a home. And I started to, from having to cook every single meal, to working 40 hours a week, to traveling around on weekends, to performing the holy month of Ramadan. Now that I've done so much this summer, I feel like I have never done this much in a period of 85 days, ever in my life. 21, back when I was 20 when I made it. Acknowledgement, a big shout out to my parents, who actually got the biggest opportunity cost by letting me actually stay here and do this work. And big thanks to other people as well for funding. Thank you.